Okay, so welcome back to the channel after almost a year of uploading, I guess. This video is going to be different in three ways. First of all, this is the first time I believe that I'm showing my face on this channel. So I guess, how many subscribers do I have? 335 subscribers, special face reveal. The second way this is going to be different is that we're not going to be doing maths, we're going to be doing some coding. And the third way it's going to be different is that I don't know these problems, I'm just recording myself attempting these problems. So I don't know how to solve them from the get-go. I'll try to solve them and show the process also. So with that, let's get to the first problem, I guess. So this is the problem. This is from division 3 problem D. It's rated 1400 and it says Maxim has an array A of n integers and an array B of m integers. You know, this Maxim reminds me of Maxime from this Despicable Me 5. I accidentally wrote 5 images. Yeah, this guy. His name is Maxime, right? So he has an array A and he has two arrays. One of them is bigger. He considers an array C of length m to be good if the elements of array C can be rearranged in a way such that at least k of them match the elements of array B. Okay. So if you have 1, 2, 3, 4 and you want to match 3 of them, then 4, 1, 2, 3 is good because of course you can like rearrange to 1, 2, 3, 4. 2, 3, 4, 5 is also good because you still have 3 matching elements, right? I guess that's what they're saying. Maxim wants to choose every subsegment of array A of length m as the elements of array C. Help Maxim count how many selected arrays will be good. In other words, find the number of positions such that the elements form a good array. Okay. So, I mean, right off the bat, one thing you can notice is that to find, like, if they match, to find if a sub-segment matches is quite easy, and there's a very straightforward trivial idea also. Okay, so wait. What the hell? Here's the problem. We have array A, okay, and we have array B, and we want to find, so let's say this is size m, this is size n, and we want to see how many segments we can pick. Let's say, so this is one subsegment, this would be another subsegment, and we want to see how many subsegments there are such that the subsegment and array B are good. And the way they're defining good is that k elements must match between the two arrays. So here's the thing, to check that k elements match is quite easy. You could of course do like an O n square search where you say that okay, so so the problem, our sub problem is to find good, like how do you find good arrays, how do you check if two arrays are good? So these are both of n length, and we want to see if they are good, and the way we check they are good or not is if k elements match. One way is to just say that okay, see the first element in array A, this is array A, array B. So you check the first element in array A with every other element and see if it matches, and you say that okay, it matches, and then you keep on counting. There's another element, you do it again and you see if it matches. And of course you have to you have to also make sure that you don't count the same. So you can say like if you found a match, then you change its values to, let's say, a -1, because I think they have told us that there are no negative numbers. So if you find a match, you can just change it to a negative number so that you're not double counting the same element. And so you can continue the same for the other element, and this would take O(n) square, because for each element you're doing like a n search. But this is like a very, I think, popular problem, I guess. Like, this comes up a lot, and the easier way to do it is just in O(n) log. I think I should really write on my iPad instead.
Wait.
So here's what I'm talking about. So I'm talking about 2 pointers, and we have 2 arrays, array A, array B, of the same size, and our question is, let me choose, do k elements match? Okay, that's our question. And just for explaining purposes, let's just fill these in. And since these are so first of all, these are sorted, right? And we sort them in n log n. So let's say after we sort, just saying some random numbers, 2, 2, 5, 6, 9, 10. Let's say this is what 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. And let's say array B is like 1, 2, 3, 4, 10, 11. So the idea of 2 pointers is that there's a pointer to each array, and you compare them. You say, okay, is 2 equal to 1? That's false. Since this is false, you ask the question, well, is your element greater, right? So 2 is greater than 1. So since 2 is greater than 1, it is a possibility that if we move our pointer forward, we might actually find 2, right? Because it's greater than 1. And indeed, we do find 2. So here we can just keep a count, and we found a match. So we say count plus equals 1. And so we found this element that matches, but also we want to make sure, so first of all, we found a match over here, so we just move forward, right? And since we also found a match here and we don't want to double count it, we also move forward here anyways. And then we ask, well, is 2 equal to 3? It's not. Then we ask, is 2 greater than 3? It's also not. So that means that not only is 2 not equal here, it will never be equal afterwards, right? So we just say, okay, just go on to the next one, and we just repeat, is 5 greater than 3? That's true. So we go here. Is it greater than 4? It's still true. We go over here. It's not greater than 10, and it's also not equal to 10. So now we move to 6. The same thing, it's not greater than 10, it's not equal to 10. We move again, same shit. We move to 10. Here we have found it. So again we do count plus equals 1. Oops, I think I erased that. So when we finally get to 10, we increase the count because we found a match, and then we have nowhere to go. So that's how you find if k elements match. That's a better way to find than n square. So let me go back to the previous screen. So the idea is that I can find if 2 arrays are matching. I can find that in n log n, and what I can just do is, this was our original array, so I can just start from here and consider this subsegment or subarray, and then I just ask, well, is this matching or not? If it does, just increase count. If it does not, don't increase count and move forward to the next one. And now you consider this array. I know this is getting really bad. You just consider this bigger. You just shifted one to the right, and then you check again. You continue till you really just reach the last part. So this would take n square log n, and this is the obvious idea that I was talking about. Now I don't know if there's a better algorithm or not, because you see we are really doing, like, there's lots of overlaps, right? Every time you just move one to the right, you add one new element and you remove one less element. So I'm thinking that maybe there's a way, maybe there's a better way that you don't have to do n square log n.
Wait.
Basically what I'm thinking is something like this. Okay, here's your array A, here's your array B. So you first take the first subsegment and you say, well, does it match, does it not match? If it matches, count +1. In either case, you see like how many elements are matching. You can keep a track of that, right? And then when you move to the next one, which is something like this, now what you do is you remove this element. Like if this element was counting towards your number of matches, you just remove this element and you put this element inside. So if it matches, then you put it in your array of matching numbers. If not, you don't put it, and you check if the length of your matching numbers is greater than equal to k. So this would pretty much take n log n, because we're not doing n work, we're just doing constant work. But the problem here is how do you, so first you need to keep a track of like what numbers are matching.
Wait.
Which is doable, I guess. But there's also a problem of like, what if there are duplicates, right? So if, let's say, the numbers inside are like 3 and 4, and the numbers in array B are like 3, 5, 6, and I remove a random number, let's say I remove 7, so it was not one of the matching numbers. It was not. So currently my array M, which is the numbers that match, is just 3. So the thing is that if this element is also 3, then I want to make sure that it's not already taken before, right?
Wait.
So it is doable, but I wonder if it's really required, because this is like 2 seconds. 2 seconds is a lot of time. I think let's just try to code this. Let's just try to code this n square log n. Why isn't it moving up? Let's just try to code this n square log n, and we'll see if it exceeds the time, then we'll try to code this one. Otherwise, this just... And now that I've run it, you can see that the output matches. So let's just submit it and see if it works. Hopefully it does, because I don't want to do any more debugging. 1955D, 1955D. If the time exceeds, I'm fine with that, because we still have that n log n algorithm that we haven't thought out properly. But if there's a wrong output, then I really don't want to debug it. Okay, seems like so far so good. It's just stuck on. Oh yeah, I fucking knew it. Oh yeah. Actually, I want to see the input on which. Yeah. So this is just a very huge array. So yes, we need to go back here and think of this algorithm.
Wait.
So I'm recording this after actually finishing the problem, because I realized while I was recording that I did not really explain properly. In fact, I made a few mistakes, so I'm just going to explain the algorithm correctly this time, hopefully. So here's the idea. Our goal is to just have something in n log n, right? And the gist of the idea is, like I explained before, is that when we have our A and our B, let's just say we're currently at this sub-array, and we move one place to the right. So when we move one place to the right, this will be our new sub-array. So basically a lot of the elements are just there. So the things that were matching are already matching. The only thing that changes is that this element is now replaced by this element. So here's the idea. We keep a track of the number of elements that are matching in B, right? So whatever matches will be in B. And in my code, B are actually the elements in the B that do not have a pair. And also we needed an A2, which were basically elements in the current subarray of A which do not have a pair, because if something already has a pair, it is already in M. So the purpose of M is just to keep all the pairs. B and A2 are the elements in B and the subarray A which do not have any pair. So here's the idea. When we move to the right, if this element that we just kicked out, if it was not in M, then we don't need to do anything because it was not paired. If it is in M, we need to check whether there's another instance in A2. So for example, let's say it was 3, 3, 2, 1, and let's say this was our current array. Actually, let's say our current array was of size 3, and let's say our B is something like 3, 3, 5, right? So currently all of these things are matched. Actually not 3, 3, 5, 3, 3, 6, 5. Okay, so currently this 3 is matched with this 3. So when we shift one to the right, we say, okay, so this was paired to something, right? We need to check whether in our unpaired numbers, which are 3 and 2, is there another 3 that is not unpaired, that is not paired. So, and if it is, so we just attach it to this 3, right? So if we do, so in short, when you're kicking out an element, if it's not in M, just kick it out. If it is in M, you need to check whether it's also in A2, because if it's in because if it is in A2, you need to keep it in M. If it's not, then yes, you just move on. And also you kick it out of A2. Like if this element was in A2, you need to also kick it out of A2. Similarly, when you're adding a new element, actually adding a new element is a bit more easier, because when you're adding a new element, you need to see if this element is in B. because B are the elements of B which are unpaired. So you just check in B if this element is in B. So if this was a 10, you just check if there was an unpaired 10 in B. If there is, you just remove it from B and you put it in M. If it's not, that means you can't find a pair, but it's still in your current subarray, so you put it in A2. So yeah, that's the idea. One important thing is, well, what data structure do you use? Because if you keep these M, B and A2 as arrays, the problem is that finding in an unsorted array is O(n), but finding in a sorted array is actually log n, and we need to do a lot of like finding and deleting. So it's better to use something like AVL trees or multisets. Actually, I think in C++ multisets are just AVL trees, because for multiset, right, multiset, finding, deleting, all of these things are log n. Creating one is n log n, but we're actually fine with that, right, because we just want n log n anyways. So creating is n log n, and we can do like at most n of these finding and deleting, so our overall runtime is also n log n. So yeah, that's the idea.
krainę zapomnienia. W głowie myśli mam, kiedy skończy się ten stan, gdy już nie będę sam, bo wiedzie biały węgiel. Tylko jedno w głowie mam, koksu 5 gram, odlecieć sam w krainę zapomnienia. W głowie myśli mam, kiedy skończy się ten stan, gdy już nie będę sam, bo wiedzie biały węgiel.
Okay, so finally, as you can see, it's accepted after a long while of debugging. Well, actually, this first time was our n square log n algorithm, which worked fine until they gave you a very big input, and then there was a long debugging session, and I even failed the test one, and eventually it got accepted. So the problem was, firstly, that I wasn't updating A2 properly. So the purpose of A2 was to keep track of all the elements in our current substring that do not have a pair, right? Like, okay, so B are all the elements in B that have a pair. Matches are elements that have a pair. B are elements that don't have a pair. A2 are elements in current A that do not have a pair. So the problem was that I wasn't updating this properly. For example, there was an insert over here too, but you don't need to insert it if it's already going in matches, right? If something is in matches, it cannot be in A2. Like, either you have a pair or you don't have a pair. The second problem, which was somehow quite hard to find, was that I was erasing everything. So you can see here that I am erasing the iterator. which only erases one single occurrence. But if you erase, so for example, if I say erase AI, it will erase all instances of AI. So that becomes a problem if you have multiple digits. So that was the other problem. And then a surprising problem was also that here all these statements that I use for debugging, apparently because these are lots of statements here, it failed to pass the time constraint because there were so many print statements. It was just failing. But yeah, eventually that's it. That's the whole thing. This problem actually took me way longer than I thought it would, and I think, I'm not sure, but I think I won't include any other problems in this video because I think just this problem is long enough. I don't know, maybe I will include, maybe I won't.